So we've still got accumulators in this chapter. So we're going to go through that today. So our learning goals are to become familiar with the different types of accumulators, because there are several ways of designing accumulators. We're going to know how a piston accumulator works, which is one of the types. We're going to know how a diaphragm accumulator works, and also how a bladder accumulator works. And those are the three main types of accumulators. We're going to become familiar with pressure vessel safety requirements. That is because an accumulator is designated a pressure vessel, so it needs to go under the laws for pressure vessels, because as soon as you have something under great pressure, you risk it blowing up if something goes wrong, so then you have to have special safety requirements for it. We're going to get to know how a single acting cylinder works also. The single acting cylinder, that's chapter 5, so we are just barely going to start on chapter 5 today before we leave off. So the hydraulic accumulators, they collect energy from the pump, so hydraulic energy is stored inside the accumulator. So they collect and store the hydraulic energy. They release hydraulic energy when it is required. So basically it is either an automated process where when certain requirements are fulfilled, then it's going to release its hydraulic energy, or it is decided by the operator of the system. Then the operator will manage the valves and tell it to, now we need to use the energy from the accumulator. So it depends a bit on what kind of system it is, but it is released when it is supposed to be released. So it's stored up and then it's kept there until needed. And accumulators can have thousands of different shapes. Most of them look something like a bottle like this, but they can have quite a lot of different shapes, basically. They are used to equalize fluctuating flow rates. So if you have a pump that's working quite jerky, so it's delivering a lot of flow and then suddenly a lot less flow and then a lot of flow again because it's not operating quite smoothly, and then you can use an accumulator to just equalize this so that you get a steady flow into your system. Because whenever the pump is delivering too little flow, then the accumulator will start delivering some extra into the system. So that's one of the uses. And also if you have devices with various fluid requirements being used, so you have many different components in your system, some of them are going to use a lot of fluid when they're in operation, and some of them are going to use very little. So this is going to take its toll on the flow from the pump, and then you can use the accumulator to just add a little when you need extra flow rate. And also if you have brief but very large fluid requirements, so that if you have a gigantic piston that's going to be operated somewhere in your system, then it could be nice to have an accumulator that assists in delivering fluid to this particular piston, because it might be that your pump can't really handle the piston and the rest of the system all on its own. So that when this large piston is in operation and the rest of the system also is supposed to function, then you need an accumulator to help run the piston. They're also used for maintaining constant pressure, so that you can basically equalize pressure peaks a little bit. Not the pressure peaks, but when you get pressure drops in your system because you are using parts of your system, so that you are losing pressure by using the system as it is designed, then they can help compensate for that. They also compensate for leakage loss inside the system, so that if you are losing pressure due to leakage, maybe you have a hydraulic motor which is very old and has a lot of leakage loss, isn't very efficient. You might have a lot of leakage loss in cylinders also, and then you can get compensation through an accumulator. and also for maintaining clamping pressure for long periods of time. So that if you are operating clamps that are basically pistons that you are using to clamp onto something, then it would be, if they are going to clamp on there and hold that grip for quite a while, it's not that smart to have it all running on the pump, because then the pump has to continuously run and run and run. Then it might actually be better to close off that part of the system and have an accumulator that is just keeping the pressure on, because then you won't have any risk of the system releasing the grip unintentionally. So for these parts up here, most of the time the accumulator won't be shut off from the system. So it will continually be receiving flow from the system, and it will also be giving off flow every now and then when it's needed, so that they are usually open to the system in this case. In the clamping scenario, it would most likely be shut off from the system if it's going to be used to maintain clamping pressure. It is also used to level off pressure peaks, so that if you get these pulses from the pump, you can level them off and get a smoother flow. And if you have very valves in your system that can switch on and off, open and close very quickly, so fast-acting valves, then you can use smaller accumulators close to those valves to sort of cushion these pressure peaks that are going to happen every time you operate the valve. Because the valve is moving so quickly from open to close that you get sort of a chain reaction happening back in. Every time it closes, then you sort of get a pressure peak there, because it hits the valve and it doesn't get a chance to sort of taper off if the valve closes fast enough. So then you can cushion those by letting the accumulator sort of absorb this pressure. And it's also an energy source for vibration-free drives, so that if you need to use hydraulic equipment for highly precise machining of workpieces, you don't want a motor and a pump connected to the system that are going to vibrate when they are running. So then you would rather run the hydraulic system, you would pump up pressure, you would fill up your accumulator, then you would shut down your system. You keep your accumulator closed with full pressure inside, and then you can slowly release the pressure in the accumulator and let it run through the hydraulic equipment that's supposed to do the precise machining. You can also use it as an energy source for emergency operations. And this is often where the manual release of hydraulic energy comes into play, so that you will have an accumulator that is fully charged in your system, and just in case that you need to use it in an emergency situation, it is usually manually controlled by the operator through valves. So then the operator will tell the system when he needs to use this. For an example, if there is a power outage. Yeah?
When you say it stores hydraulic energy
Yeah?
in the system, I'm quite confused if it's the hydraulic or the pressure in the system. Pressure energy in the system.
It's a combination. It can both store pressure energy, but it can also store fluid, so that if you have a really large accumulator, you can have quite a lot of fluid flow from it. So you can store a lot of fluid in it under a certain amount of pressure, anything to what the accumulator has been designed for. And then you can release this hydraulic fluid under the pressure that it's at inside the accumulator. So the pressure will slowly drop as you're releasing it until there is no more pressure left. But if it has been correctly designed according to your hydraulic system, then you will have enough to perform these operations. So you will have enough both fluid and pressure inside the accumulator to get to do what you're supposed to do. So examples of emergency operations is in a production facility, for an example, if it's one of these automated production lines where you have a lot of things happening along the production line, you can design your accumulators to be able to complete one production cycle, so that if something happens and you stop producing at one point, you still have to get the rest of the stuff that is halfway through its production. You still have to get it through the rest of the production line. And you can do that using accumulators. So if you have designed it correctly, you will have enough pressure and flow to run all of the system until all of the work pieces that have begun its production are finished. So that's one of the uses. And also it is, for an example, on ships for closing or opening bulkheads. If you suddenly lose power on the ship and your pump isn't running anymore, so you don't have any more pressure, they usually have designed accumulators that are capable of either closing or opening the bulkheads if need be. The bulkheads are these internal doors, basically, in the ship. So often it's, I'm a bit unsure. I think they are. I'm not going to say this completely for sure, but I think they are meant for closing off sections of the ship if you have a leak in the ship. So that instead of like the Titanic, where everything just rushed in and you had a ship sinking, they can sort of section off parts of the ship with these bulkheads so that they contain the leakage inside a small area so that they can keep floating. And of course, in such a situation, if you've hit ground or anything, you would very much like to be able to operate them. And if you've hit ground or something, it might very well be that you have also lost your power. So then it's good to have these accumulators that can run everything. And actuating brakes or doors in case of emergency, that is also one of the things they can do. So that if you have a system that is running, for example, in a mine, you might have a system running on tracks, so railway tracks, more or less, and you could have hydraulic braking systems on them. And if you lose power in your pump, you still want to be able to brake, not just have it run rampant along the lines. So then you can have compensators ready, so that if the pump stops delivering the correct flow and pressure, then you can use the accumulators to still use your brakes to stop the vehicle. So then for the hydraulic accumulators, we are using hydraulic fluid inside it, and the hydraulic fluid is, for all intents and purposes, an incompressible fluid. We have to get really huge pressures in order to be able to compress it at all. So within the pressure ranges where we are working with hydraulics, usually up to 600-700 bars, then it's an incompressible fluid. It won't act like a gas. And this means that we can store energy in the same way as we would in a pneumatic or gas-driven system. In a gas-driven system, we would simply store it in a pressure container. We could get enormous amounts of volumes compressed down to a very high pressure inside a fairly small bottle, just like a regular tank of air or CO2 or whatever. That's not something you can do, since we can't compress the hydraulic fluid down to a smaller volume. We can't store it that way. But what we can do is we can have hydraulic fluid inside a container, and we can load this container either with actual weight on top of it, so that it's pushing on the hydraulic fluid, or we can use powerful metallic springs that are also pushing on the fluid, creating pressure, or we can use a cushion of gas in some way inside this container that will also exert pressure on the hydraulic fluid. So if we're using a cushion of gas, it is called a hydropneumatic accumulator, and they use a separator between the hydraulic fluid and the gas. Of course, they don't want to mix the gas and the hydraulic fluid. That would be bad for the system. You would get bubbles in your system, and it wouldn't be good at all. And usually, they are separated using either a piston, a diaphragm, or a bladder. So those are the three ways that they separate the gas from the hydraulic fluid. And here is a small section of an accumulator that doesn't have any separator. So here we just have the fluid at the bottom. We have a connection between the gas and the fluid there. So you might end up with having gas being absorbed into the hydraulic fluid and then transported around the system, which is not a good way of doing it, but this is basically the way they designed the very first accumulator. So this is how they started off. Then we have the types that are using a bladder inside them, so that they have the gas contained inside the bladder, much like a balloon, basically. But it's a more the bladder material is quite a lot more has a lot more strength in it than a regular balloon would. But it is also flexible, so that you can fill up. You can let hydraulic fluid enter from the bottom, and it can fill up here and really compress the gas into basically just a very small ball inside the bladder. And then you can release hydraulic fluid again, letting the bladder expand with the pressure of the gas inside it and just forcing hydraulic fluid out of the accumulator. And then you have the piston type. And there are many ways that those can be constructed. Some use gas, where they have hydraulic fluid on one side of the piston and they have gas on the other side of the piston. It works in exactly the same way as the bladder, that if you start filling in hydraulic fluid at a certain pressure, it's going to move the piston upwards, compressing the gas, and the gas will gain more and more pressure the more it's being compressed. And then if you stop adding pressure to the accumulator and then you have to use the energy inside the accumulator, the gas is going to force the piston downwards again, so it's going to push the hydraulic fluid out of the accumulator. It can also be spring-loaded instead of using gas, so that's the one we have here with springs, or you can basically just have a dead weight on top of it, so that you're filling in hydraulic fluid at the bottom, and then you have a dead weight connected to the top of the piston, so that it will force the piston downwards once the force from the weight becomes greater than the pressure inside the cylinder, it will start forcing the hydraulic fluid out. But one thing is very important when we are using cushions of gas in them. We can't use air and we can't use oxygen inside it. So preferably we use nitrogen in them. That's the most commonly used gas. And of course the air and oxygen has to do with this flame triangle. We don't want to give the hydraulic system the ability of having both heat, fuel in the shape of hydraulic fluid, and oxygen. So we are basically just denying the system one of the parts of the fire triangle. So here we have a cross-section of a piston and a diaphragm and a bladder accumulator. And we're going to look a bit at different pressure values. They have certain names for different pressure values for these. So we have a transport pressure, which is basically the gas, the pressure of the gas inside the bladder or the diaphragm or the piston during transport. So this is after it has been created and made in the factory and is going to be transported to wherever it's going to be installed in a system. Then it's usually around 10 bars in there. So it sort of has a pre-pressure of 10 bars. And then we, as it has been installed into the system, we preload it even more. So we start filling it with even more gas when it's placed inside the system. And then it's filled exclusively with the gas, and usually around 10% less than the smallest working pressure of the system. That is because you don't want your accumulator to be able to push back, no matter if you're working at your pump is delivering the smallest working pressure in your system. You don't want your accumulator to be able to push everything back so that nothing is going to be compressed in here, because you have a higher pressure inside the gas than the hydraulic fluid that's entering the accumulator. So you want the pressure of the gas to be lower than the smallest working pressure of the system, or else the pump basically won't be able to fill the accumulator. So if you have, just to give an example, if you have 100 bar in your system, so your pump is delivering 100 bars of hydraulic fluid in here, then if you have 110 bar pressure inside your bladder, the bladder isn't going to be compressed. So it's just going to stay there because it has enough pressure to stay fully extended. So that's not going to work. But if you have 90 bars of pressure inside the bladder, it's going to slowly compress it. And if 100 bar was the lowest working pressure of your system, and you can boost it up to 150, maybe 200 bars, then you are really going to compress the bladder and start filling up all of the area here with hydraulic fluid that can be released. Yeah. Yeah, we're going to look more at the diaphragm afterwards. So, then we have, of course, the smallest working pressure, P1. So that's the one in the system, the one where the preloading pressure has to be 10% less than this one. And the smallest working pressure can be calculated beforehand when you're designing the system. But if it's an old system that you are doing some design work on, maybe you are upgrading a system or something, it might just be empirical, that you've just basically measured it with a pressure gauge. So what is the smallest working pressure delivered into the system? Then you can just check your pressure gauge if the system is already operating. And then the largest working pressure, that's set for the pressure relief valve, or it's calculated to what the pressure relief valve has to be if you are designing the system. So if you have a system with an operating pressure of 200 bars, and you have a pressure relief valve set to 210 bars, so that it's going to release pressure back to the tank, release fluid back to the tank if the pressure exceeds 210 bars, then that is going to be your largest working pressure, the 210 bars. And you will have gas loss both through the diaphragm and through the bladder. You can actually have gas loss in the piston also, past the seal there. So that is also a possibility. It's going to be very small, but it is a possibility that it's going to happen. It will be small enough that most likely your filters and your tank is going to, either your tank is going to dissipate it or something like that. So you won't really notice it in your system. You're not going to get large bubbles in your system or anything. Oops. But it is important that you check that you have regular servicing intervals where the pressure of the gas inside the accumulator is checked, just to see that it is within the operating range. Now we're going to look at the piston accumulators first off. So at the top we have a valve for the gas, because we already know that after it has been transported and installed into our system, we have to preload it with more gas. So we need to have a valve to be able to add gas to the system. And we need to have a cap to stop the gas from escaping. And we need, of course, a cylinder barrel to keep all of this in place and make a tight fit to the piston. And then we have basically a floating piston. So this is a bit different from what all of the cylinders that we've looked at earlier, because we are used to seeing a piston and then we actually have a rod coming out of the cylinder. But this one doesn't have that use, because that's not what we're going to use it for. We just need a barrier between the gas and a movable barrier between the gas and the hydraulic fluid. And of course we need a cap on the hydraulic fluid side also, because we need to keep the hydraulic fluid inside. And then we have a port going to a valve set, usually. And we have some typical characteristic values for the piston accumulators. So we have volumes from very small, 0.2 liters, up to 650 liters. So with a very large piston accumulator, you can run quite a few operations using your system after the pump is out of order or something. You have the possibility of monitoring the piston level, so you can actually have a monitoring system outside the piston accumulator, which tells you the level of the piston, so that you can actually see how far up have you compressed the gas, or how little hydraulic fluid do you have left in your accumulator. Which is, for an example, if you are using it as an emergency power supply for running a production line, so that you know that you need approximately 400 liters of fluid flow in order to finish this production line. By knowing where the piston is, you can know how many liters of fluid you have left in your accumulator, so that you will be able to know if you are going to make it all the way to the end. The piston can, of course, be replaced. We can disassemble the caps and take it all apart, and it's going to be very easy to switch out the piston with another one, or just exchange the seals if they have been broken. And the maximum permissible pressure ratio for this one is nothing. You can have enormous pressure differences on each side of the piston, and that is basically because the piston is made of steel, so it has quite a lot of strength, so you're not going to deform anything. What's basically stopping you here is the maximum pressure of the system, because your cylinder barrel and your end caps, they have to be dimensioned to handle the maximum pressure of the system. But whether you have 600 bars on the gas side and 10 bars on the hydraulic fluid side, it's not going to matter. So the difference in pressure doesn't matter at all. It's just the maximum pressure that affects it. So P2 was, of course, the largest working pressure that we have, the largest pressure that we're going to have in our system. P0 was the preloading pressure, 10% less than the smallest working pressure. And one of the good things with the piston accumulator is that you can have large volumes, and you can release them very quickly also. Because the only thing stopping this piston from moving very quickly down is how fast the hydraulic fluid can escape from the accumulator through the system. So basically the flow is what's going to stop it. You will have a very tiny friction loss over the seal there, but that's more or less negligible. You won't be able to notice it or measure it in any way or form. And it's often used in die casting machines, where you need you need very high pressures, and you often need quite large flows. And you can utilize the full length of the piston accumulator. So you can, as you can see here, it's once the piston is up here, if you push the piston all the way up, the gas is going to fill exactly this area. So you can utilize, if you have a really large piston with 650 liter volume, a really large accumulator with that much volume, you can fill almost all of it with hydraulic fluid. So that's very positive for it. Now we have a clip showing how they work. Where's the mouse? There it is. So this is from Parker, which is a very, very large international supplier of hydraulic components. So now they're going to pre-charge gas into the accumulator. So now they've fully charged it with the blue gas up there. Then they start pushing fluid into the accumulator. They compress all of the gas, more or less. And then when you require oil, the gas is allowed to expand so that you push the fluid out again. And then you can repeat the cycle back and forth as much as you want, basically. And you can imagine that this works really, really fast, so you can get a very quick release of everything inside there. Let's see. So then we're going to look at the diaphragm accumulator. And this one also has a gas valve up top, of course, because you need to preload it with gas. It has a pressure vessel, which is usually shaped something like that, so it looks like a cross between a bottle and a ball, basically. And it has this black part here, which is the diaphragm, which is usually some sort of rubbery substance that is used, so it can be deformed by the pressure. There is a valve disc at the bottom here, and the point with this disc that is built into the diaphragm is basically just to protect it from the sharp edges of where the hydraulic fluid is entering. So just to make sure that these edges won't make any cutting damage into the rubber. And then it's connected to a valve at the bottom, which allows the hydraulic fluid to enter and escape. And typical characteristic values here, 0.1 to 10 liters. So these can't be they can't be all that big. So 10 liters, that's the usual bucket that you will have at your home. So it's not all that big. It is not possible at all to monitor where the diaphragm is, how much it has been compressed or anything. And the diaphragm can be replaced if the accumulator has been screwed together. So if the pressure vessel consists of two parts that are screwed together somehow, then you can exchange the diaphragm. But some of these pressure vessels will be welded together, and then you can't exchange it at all. So the maximum pressure ratio is between 4:1 and 8:1, so that you can't really have that much of a difference between your largest working pressure and your preloading pressure in these. So they are more used for the smaller tasks where maybe you are just going to operate the pilot pressure of a valve or something. So it doesn't require much fluid because you have a maximum of 10 liters available, and it doesn't really require all that much pressure. It just needs a little bit to be able to work. And as mentioned, they are either welded or screwed together. And the diaphragm material, it really depends on which hydraulic fluid you are using. So that with some of the special flame retardant fluids and stuff, it might be necessary to use a different diaphragm material to avoid it being disintegrated by the fluid. And of course with the operating temperature also, because with all rubbery substances, you are going to operating temperature has a lot to say for the lifetime of the material. So it's if it's a high operating temperature, the rubber will probably have a lower lifetime expectancy than if it's a regular operating temperature. And they are highly efficient since the diaphragm itself is very flexible, so that they move very quickly when they need to move. And they are practically inertia-free, so that you have no friction loss at all, because the only thing you're doing is deforming the rubber. You are not moving the piston along the cylinder wall, so you're not getting any friction, dynamic friction along along the seals there. And also with inertia-free, the diaphragm basically doesn't weigh anything. While a piston made of steel, it's going to have some weight, so it's going to have some mass that needs to be accelerated. So it has a little bit of inertia there. And the nice thing about this one is that it can be mounted in any desired position. So you can have it upside down or whatever you want to. So it doesn't really have any restrictions that way. Here we have a small clip showing how it works. So now they're adding pressure to the system, and the diaphragm is being deformed. So you have the gas up top here. And when they release pressure from the system, the diaphragm just forces the fluid back down here. So before the break, we're just going to look at the bladder accumulators also. I've talked to the IT guys about this black screen happening all the time, but they knew that it was happening, but they had no idea why. So hopefully they can try to fix it during the semester. So the bladder accumulators are the ones with the balloon inside them. They also, of course, have a gas valve up top to allow for preloading of gas pressure. And they have the pressure vessel, which usually looks like a gas tank, a bottle shape. And they have this flexible bladder that is placed inside it. They have the so-called non-return valve. It is also called poppet valve many places. So that one is there to protect the tip of the bladder so that it's not going to get any damage from the edges there. So it's usually, at the top here, it's usually hollowed out so that the tip of the bladder here, it fits down into the hollowed out part of the poppet valve. And by the time the bladder has pushed the poppet valve all the way down, it has a tight seal along the edges here before the bladder sort of expands over them, so that it's not going to get any damage from it. And then, of course, we have the fluid port in the end here, that all of this area here allows for fluid to pass through it. And the typical characteristic values for it is 1 to 50 liters. So here we can have a bit more of fluid stored inside it. So that's a plus. Again, it's not possible to have any way of monitoring the position of the bladder. Only way that would be possible was if you made it in some kind of see-through material, the pressure vessel, but that's you wouldn't have enough strength to handle the pressure then. The bladder can fairly easily be replaced. Actually, you can dismantle the top here and then you can just pull it out. So it's very easy to replace it. And the maximum permissible pressure ratio is 4:1. So this one has an even lower pressure ratio between the largest working pressure and the gas preloading pressure than what the diaphragm had. So the diaphragm usually had from 4:1 to 8:1, while this one has maximum of 4:1. And again, highly efficient. The bladder is very flexible, so that it's not going to be a problem using it. It works very quickly. And this one, like the diaphragm, is also practically inertia-free. You don't have any sliding parts. You're just compressing flexible material. But this one usually has to be installed like this, in a vertical position, with the fluid coming in from the bottom. And that has to do with how the bladder itself is going to behave while it is being compressed and expanding. So in order to have it behave guaranteed without any sort of failures, then you want it in this position. You can mount it in other positions, but you do have a chance of something happening that's going to cause it to fail in operation. And then we have a clip. This one is also from Parker. So you see it sort of looks like a gas tank. Now they're pre-charging the bladder with gas. And it expands until it hits the poppet valve and closes it completely. And then it fills out the entire tank. And then they let the hydraulic fluid under pressure enter the accumulator. And then when they release the pressure on one side, it's going to push out as much as it can. And this works really quickly, so it doesn't. You can have quite a quick release of your hydraulic fluid in there. Right, we'll do a 15-minute break, and then we'll look at safety regulations. Okay, so then we'll continue with safety regulations. As I mentioned when we started off, the accumulators are regarded as pressure vessels since they are containing quite a lot of pressure in them, and they are also, they have gas under pressure in there, so it's very compressed. If the gas valve, for an example, should be damaged so that it is pushed away and the gas is released, it's going to expand very, very suddenly, and that's basically going to cause an explosion. So that it is very, very dangerous to handle these accumulators when they are pressurized. And one thing that is with pressure vessels is that there is going to be absolutely no welding or drilling on the accumulator itself. So that the pressure vessel itself of the accumulator, you can't harm that in any way. You have to leave it completely intact so that it maintains its strength. And this is, of course, since they are classified as pressure vessels. And this is an excerpt from one of these standards that go for pressure vessels. I think it's it's a German standard on this one, but usually more or less the same goes into the ISO system when you look at pressure vessels in the ISO system, and also in the American systems of the American Society for Mechanical Engineers, the ASME. They also have pressure vessel codes. Those are even more extensive. It's like this thick when you have them on a bookshelf. It's really a lot to handle. But this is just a very quick excerpt of some of it. So they are classified into groups, given numbers, so 1, 2, 3, stuff like that. In this one, we're going to look at group 2 and 3. And for group 2, we have pressures that are greater than 25 bars. And we're going to have a pressure volume capacity that is less than 200, basically. And for group 3, we have a pressure greater than 1 bar. So group 3 will be between 1 bar and 25 bars. So then you have very low pressure in group 3, and then you have higher pressures in group 2. And then, of course, if group 1 had been in here, you would have even higher pressures there. And here you have a pressure volume capacity between 200 and 1,000 liters on these. So there are a lot of tests to be done before the accumulator is ready for use. So the manufacturer for a group 2 a pressure vessel, they have to do pressure tests, and they have to certify that it has been properly manufactured and that it fulfills all of the specified requirements in the standard that they are going for, whether it is this German one, which is Drückbe, or if it's ISO, or if it's the ASME, whatever it is. It has to fulfill the specified requirements. For group 3, pre-testing is done by an appraiser, so it doesn't necessarily have to be the manufacturer itself, so they can just hand it to a company that does tests. And again, it has to be certified that it's properly manufactured and that it fulfills the specified requirements. But of course, for the low pressures in group 3, the requirements are a bit easier to fulfill than it is for group 2. It has more strict requirements. And then it also has to be tested by the operator. So whoever is going to use it has to test it before they start using it. So then an expert, and that is usually classified as someone employed by the operator that has extensive experience using this kind of product. That is the usual classification of an expert. So it is just a regular employee, so most likely one of the technicians that are working with the hydraulic system, who has enough experience to know how the hydraulic accumulator is supposed to behave, so that he can run tests on it and see that it works as it is supposed to. So he's going to test it to the approved pressures, and certify that it works as it is supposed to work before they actually start using it in their system. And again, for group 3, you can have an appraiser doing it. So it's slightly less strict when you have a group 3 one. And also in group 2, you have the points where it needs to fulfill the requirements specified in the scope of that respective tests of how it is being tested, while for group 1, it is just to certify that it is in good condition. There's no visible damage in it, and it works as it's supposed to work. So that's basically just the very quick test that is done for group 3. But then they also have to do periodic tests on the pressure vessels. And for group 3, again, an expert, so you have to have someone with experience with these systems to do it. And it has to be determined on the basis of this expert's experience with the company's way of operating. So there is no point in having a monthly test if this hydraulic system is in use every other month. You don't need to test it more often than you're using it. So then the expert has to decide that, well, then I'm going to test it every 4 months instead, since we're not using the system that often, for an example. And periodic tests for group 3 is the same as group 1, but I'm fairly sure that you don't have the expert requirement on group 3, but in the book it says it's the same as group 2, so we're going to run with that. Then we're going to look a bit at safety equipment, so the ways we can keep the accumulators safe when they're under pressure. So we have minimum safety requirements for the accumulators. So we're going to need a pressure relief valve so that we don't exceed the maximum pressure allowed. And it's going to be tested and sealed in the factory after it's been produced, and a pressure certificate is going to be included. So the only thing that the pressure relief valve is going to experience before it's put to use is that it's going to be installed into the system. So no one's going to pick it apart and then put it back together again, because then the pressure certificate will no longer be valid. So then you have to basically send it back to the production facility or someone who is approved by the production facility to disassemble it again and then put it back together and certifying that it's been done correctly. And it needs a stopcock for the pressure supply port, so you're going to be able to stop it. And you also need a drain cock for the tank port, so that you can drain the fluid afterwards. And you're going to need a pressure gauge, because you want to keep an eye on what pressure you have in the system with the accumulator. You need to know that it's not exceeding, because even though the pressure relief valve has been tested and sealed and certified that it works, something might still happen that causes the pressure relief valve to not open when it hits the maximum operating pressure. And then it's very important that you have a pressure gauge so that you can suddenly see it's supposed to open at 210 bars, but now we're up at 220. We have to do something to stop this, or else something's going to blow in the system. And these minimum safety requirements, they also have requirements to identification. So the date of manufacture for the accumulator, so that has to be, usually it has to be hard stamped somewhere on the accumulator. But it might also be that it's sort of a plate that's been screwed onto the accumulator with bolts. It needs a serial number. Also, again, hard stamped or screwed on with a plate. Usually it is done in such a way that it is hard stamped first, and then this sign plate is screwed on top of the hard stamping. That is because hard stamping can be difficult to read, because basically you are just stamping in dots to create letters and numbers. So sometimes they can be difficult to read, but you are hard stamping them into the material so that they are there, because the hard stamping can't disappear. So if you're going to disappear it, you have to manually go in there and grind it away, and then you know that someone's been doing something they're not supposed to do. While having a more readable sign plate, that one can end up disappearing somehow. But then you still have the hard-stamped serial number and everything on the material behind the plate. It also needs to have the capacity in liters of the accumulator. And it also needs permissible temperature range, so that this is written directly on the accumulator, so that you know there is no way that you can sort of misunderstand what temperature range and the capacity and everything of this for the accumulator. And for group 2, they must also be equipped with a pressure vessel safety block. And this is the symbol for a pressure vessel safety block, given in the book, where you have, in this case, this is the symbol for a diaphragm accumulator, given here. An accumulator will be this oval, this slot shape, always, but it is the symbols inside there that will tell you exactly how it works, if it's a diaphragm or a piston or a bladder. It will also have a pressure relief valve. So built into this block, there is a pressure relief valve. So it is basically built into the entire accumulator. And you have the directional valve, which can open up to allow pressure into the system, filling up the accumulator, and then when it hits the maximum pressure, it will be released by the pressure relief valve. And you can also move it the other way, so that you release the pressure inside the accumulator into your system instead. And then you have the pressure gauge that you have to have in here. That's that one. Then we're going to start looking at different kinds of drives. And the ones we're going to look at firsthand are the hydraulic cylinders. Yeah. What do you think? Where? No, this is just general hydraulic systems. You can use it anywhere where you have a hydraulic system. So there are hydraulic accumulators in use subsea also. So you can find them there also, but they are used everywhere in hydraulic systems. So it's not specifically for subsea use. So they can be used. For quite a lot of different tasks. So, we'll be looking at hydraulic cylinders first of all, and they are used to convert hydraulic energy into mechanical energy, so that we can convert the pressure we have in our hydraulic fluid and the hydraulic fluid flow into something mechanical, and basically that is something moving, so that we have we can generate motion in straight line, which is also why they are often called for linear motors. So they usually when we're thinking about a motor, we're thinking about something that's rotating, but these are also motors because they are generating linear motion. And we have two general types of hydraulic cylinders. We have the single-acting ones, which we are going to look at today. And we have double-acting ones, which we are going to start looking at next week. And cylinders come in all shapes and sizes. You can really have them more or less. You can buy them directly from the suppliers in almost any shape or size, but you can also specifically design them to fit completely perfectly into a system. Of course, that is going to be very expensive to have made, because these that you will get from a regular supplier, they're made in thousands upon thousands and thousands of numbers, so that They have ready-made production lines. They are creating a lot of them in one go so that they are very cheap to buy when you're buying them. While if you are custom designing valves for a specific use in a system, maybe you only, no, not valves, but cylinders for use in your system. A custom-made cylinder that you're going to use in your system, it's probably going to be made at the tops a handful of times that it's going to be manufactured. Then that's going to cost quite a lot because you have, instead of going to a supplier who has ready-made production lines producing everything, you have to go to a specialist instead, and they have to create each of the parts individually, one by one, and that takes a lot more time and it's a lot more costly, and you also have a lot of engineering work going into designing a special design of a custom cylinder. We actually had a cylinder design which was at the Imenco when I was working there. It was from a supplier which delivered it to us, but it was almost a one-off sort because they were sort of combining a few different cylinder parts. So they were making a much shorter cylinder than what they usually did in those diameters and everything. So it was a very custom design on their parts. We, the engineers in Imenco, we didn't have to do anything of the design work of the cylinder itself. The supplier supplied us with that. We only had to specify the stroke length and the diameters necessary and things like that. But those cylinders became very expensive compared to if we could have used one of these standard solutions. So if we could have used the standard solutions, it would have been a lot better than what we ended up with. So it became a very expensive product in the end, what was made there. But that's sometimes the problem. If you need to design something that is very special, you often have to sort of accept the fact that it's going to cost a lot of money. The problem is the economics department in your company going to accept that? Are they going to accept that the stuff that you need to buy in order to make your design work, that it's going to cost a lot more than what they're used to? Is that going to be okay for them? Probably not, but usually you get a chance to at least create a prototype. And if the prototypes work well and this ends up becoming a product that most likely can be sold on, you can start selling it at higher numbers, then you could make this special cylinder into a production line where you get quite a lot of cost reduction if you're suddenly going to the supplier and saying that this special cylinder that you made for us that cost 500% more than what's usual for a cylinder of roughly the same dimensions. If you make 1,000 of them for us, what's going to be the cost difference? And then probably you're going to be down to 150% of what the regular cylinder is, because as soon as you start adding some numbers to the amounts they're going to create, it gets a lot cheaper to create it. So it's pretty amazing. We even had, right before I stopped working for Imenco, we started moving a lot of the production to production facilities in China. And it was pretty amazing. Instead of creating 50 to 100 units of a certain product in Poland or Norway, actually it wasn't always Poland that was the cheapest. Sometimes it was actually cheaper in Norway. It depended a bit on how much work the Norwegian manufacturers had. If they were filled up with work, they could basically charge whatever they wanted because they had work. But if they had free spare time on their machines, they didn't want their machines standing there not doing anything. So then they would drop their prices quite a lot, so that it became a lot cheaper to produce stuff in Norway. But still, moving production to China, and you suddenly had just a 10th or an 11th part of the cost in production. But then you were suddenly producing 1,000, 1,500 units in one go, instead of just creating 25 to 50. So it's pretty amazing when you start creating these large numbers of units. You usually get very good prices from the manufacturers. Here's an example of a very large cylinder. You have a guy standing over there, so this is a really huge one. A very thick piston rod and a very long one. So I'm guessing this is something used either on a large factory with some die casting or something, or it's used offshore on a ship or on a platform or anything. So just considering the size of it, it's not something that you would usually see on land. So then we're going to look at the single-acting cylinders and how they work. And on a single-acting cylinder, it's only the piston side that is pressurized with hydraulic fluid. So it's only the chamber where the piston is. It's not the chamber where the piston rod is. So we're going to show that in a minute. This means that a single-acting cylinder, it can only perform work in one direction because it can only add pressure to the cylinder in one direction. For the return part, the hydraulic system isn't going to do any work at all. It's just going to open all of the ports back to the tank so that the fluid can be pushed back into the tank. So this is an example of a single-acting cylinder where we have the pressure chamber here on the piston side, and here is the rod that is going to be extended out. This is a bit of a special one because it's a plunger type cylinder, so it's not the one that you are used to seeing on drawings where we usually draw the cylinder like this, where we have the piston. We are putting our hydraulic fluid in here. It's going to fill up pressure here, and it's going to push the piston over here. In this one, the entire piston is the rod, basically. That's why it's called a plunger, because you basically just have a shaft going in here. You don't have a piston and then a rod connected to it. So again, just like with the accumulator, the piston accumulator, we're going to need a cap at the bottom because this part, the cylinder itself, is going to be manufactured as a tube, basically a pipe. So you're going to need to close off the bottom end somehow, and it has to be strong enough to hold in all of the pressure that you're going to put in here. You're going to need a vent screw up top here. We'll get back to that in the next lecture, exactly what these vent screws are for and everything, but it is highly necessary to have them in the cylinders. And then you have the piston rod itself, in this case the plunger. And you have the cylinder itself, the barrel. And then at the end here you have what is sort of a combination of an end cap, a combination of the cylinder top, basically, and a guide for the piston rod. So if this had been a piston and a thinner rod going out, then this one would have been more like a cap with just a hole in it for the piston. And of course you're going to have a seal on the piston, and you have to have this wiper ring on the tip in order to avoid too much debris and dust and stuff being pulled back into the cylinder. Because if you didn't have the wiper that's sort of gathering up all of the dust and foreign particles there, they would have been pulled in here, and then they would have hit the seal, and they would have created damage on the seal, at least fairly large, sharp dust particles and stuff like that. It would destroy the seal pretty quickly, and then you would have risk having a lot of leakage out there. Not that much leakage in this case because you're not going to have any fluid, hydraulic fluid coming into this area, but then in a double-acting cylinder, which we're going to look at on Wednesday, you would have a lot of pressure loss going out here, and you would have hydraulic fluid everywhere. It would leak out. And the symbol, when it's a plunger cylinder, then the symbol is like this. So you have a very thick one. and I have the, there it is. So when it's the plunger like that, you can see the thickness of the piston rod on the cymbal, while on a regular, if it was a regular single acting one, it will look more like this if it had a separate rod instead of just being the entire piston. But those are, when you have a single acting cylinder, these, the plunger type is very common because they're very easy to create. You don't have to have two different parts here, you just have to have one big shaft instead. So it's a bit easier to make them. So when it's working, we have hydraulic fluid flowing into the chamber here. And that's going to create pressure inside here, which is going to act upon the surface of the cylinder on this end. And once that pressure becomes great enough, it's going to overcome the resistance of the piston. So it's going to start pushing the piston outwards and advancing it all the way to the end where it stops. And when the pressure is cut off, the piston is returned back to its starting position. And that's done either by dead weight, that usually these are often used to jack up cars, for an example. So you use them, you basically have all the weight of the car on top of the plunger. So when you release your pressure on this side, you have 1.5 tons pushing down on it from the car's point of view. So that's going to return it back to starting position with no problem. It might also be spring-loaded, so that's more often the case in these ones, that you would actually have a spring in here. So that you would have a piston, you have a piston rod, and around the piston rod you have a metal spring that's going to push it back when you release your pressure. And when you're pushing it back, the hydraulic fluid gets forced back through the return line and into the tank. So then you've basically just opened up your valve so that you have a free flow going back into your tank, and the tank is at atmospheric pressure, so everything is just going to return back to the starting point. So there are, as we have already seen, there are several types of these. So you have the regular piston and rod, which is this one. And you also have the plunger one, which is this one. And you have telescopic ones, which I'm going to, The telescopic ones, they allow for larger strokes because even though the barrel is fairly short, it's going to work like a telescopic rod, so it's going to go step by step and become longer and longer. So it can reach quite a lot longer than the barrel itself of the cylinder. Yeah, and this was just to show that this one is a plunger. So for the telescopic ones, I'm going to try to show it a bit better here. We do go a bit more into it in the next lecture, but I could just do it here. I have plenty of time, I see. So, so for the telescopic one, you often have several stages. There approximately, and now I'm at that one, and then we go there. I can't go all the way there. Yes. So what's going to happen is, as you fill pressure in here, this first part of the piston is going to be pushed out. And as it's being pushed out, when it hits the end, the ring going around here is going to hit the ring out here. It wasn't quite that spot on when I was drawing this one. So they're going to get contact in there. And as soon as they have contact there, the middle part, this one, is going to start moving outwards. So that one is also going to continue outwards until the ring that is in this end hits the ring in that end. And then the last part of the telescopic cylinder, the part here, starts moving outwards until it hits the end of the barrel. So then you suddenly have a stroke that is almost 2 times farther than what a regular cylinder would have had with the same length. So this means that you can sort of compact your cylinder quite a lot, and it's great to use, for an example, in a dump truck that's supposed to be able to lift up its loading area on the plane on the back of the truck. So instead of having really huge cylinders, long ones that you somehow have to manage to place into that system, you can have a telescopic one placed underneath it that's going to extend much farther than the length of the barrel itself. So then you can get it to lift high enough for all of the load to run off the trailer there. And we have a clip of one of these plunger cylinders, just showing how it works. And this is a typical one used for jacking up cars. So you enter the pressure in here, and it's going to send the plunger up. So when you release your pressure, the plunger forces it down again. So I think we'll run it once more. I thought it showed several cycles, but it didn't. So you connect your system, you add the pressure, it forces the plunger upwards. Then when you release your pressure, whatever weight is on top of the plunger is forcing it downwards, and when it's moving down, you are pushing the liquid out of the cylinder. And single-acting cylinders are often used in scissor-type elevating platforms, for an example. So it's a commonly used type of cylinder in that case, because just the entire plate and everything here is going to be enough weight that as soon as you release the pressure inside the cylinder, the weight of the platform itself is just going to push it all down. So it's going to return to the starting position no matter what you do as soon as you release the pressure. So it's very good to use in these sort of, when you're lifting something vertically. Even though in the case of a scissor type elevating platform, the cylinder itself isn't going straight vertical like the plunger one we just saw. This one is, once the scissor elevator is almost all the way down, this one will be nearly horizontal. So it will be almost horizontal when it's down there. But the point is, due to the scissor effect here, all of the weight pushing straight down is going to be pushing straight into the cylinder no matter what. So when it gets down to being almost flat and the cylinder is almost horizontal, then the force is still going straight into the cylinder due to the lever and momentums going through these scissor arms. But it is the basis of these single-acting cylinders that you usually use the gravity some way in some shape or form in order to push it back into the cylinder. So the applications are for lifting, for clamping stuff also. If you have a clamp that's going to be able to hold on to something, but you don't necessarily need to remove the clamp hydraulically afterwards. It is enough to just release it so that you don't have pressure holding it anymore. Then that's going to be enough having these. Also for lowering stuff, they can be used for that. And then often you are just in a controlled manner releasing the fluid from it. So you've built up the pressure, getting something high up, so the cylinder is fully extended. You have something that you're going to lower down, for an example, on top of a platform like this. And by controlling the flow of fluid out of the cylinder, you are going to let gravity basically just push it down. And if you feel that it's moving too fast, you just restrict the flow from the cylinder and it's going to go slower down. So that's a good way of using it for lowering stuff. Usually you have them vertically installed, and that's when you use gravity to execute the return. And almost always when they are horizontally installed, you have this spring system in them, so that you use mechanical force through a spring to return the piston back to its starting position. Oops. And for hydraulic presses, where you're using them in production, where you're actually pressing something together for an example, in a casting, where you're pressing two molds together when you are casting something. They are usually, the molds themselves are usually so large and heavy and require quite a lot of force, so the cylinders push the molds together, but then you have separate cylinders that will push them back again. So instead of having what we're going to look at next lecture, where you have the double-acting cylinders, which can push both ways, you use two sets of single-acting cylinders, so one for pushing it out and one for pushing it back. That has a bit to do with what kind of power you can get from it, and we're going to look more at that next week when we look at the double-acting cylinders. But just to sort of refresh pressure formulas for you, we of course have, if we want a force, we're going to have a pressure and we're going to apply that pressure to an area. That's going to give us a specific force. And the thing is, when we are using these cylinders, the area that we are applying pressure to is the area of the piston. But for a double-acting cylinder, you have a piston rod on one side. So you can't have the same, you have a smaller amount of area to have your pressure working on this side than you have on that side. So that means often, for an example, in the hydraulic presses, if you're going to use a double-acting cylinder, you won't get as much force pulling it back as you got pushing it in. And that means that you are basically better off using two separate single-acting cylinders, so one for pushing it in and one for pulling it back, because then you get full force on both of them. And hydraulic presses, they are pretty amazing. If you go on YouTube and just search for a hydraulic press, you're going to find many hundreds of videos where they have put all kinds of stuff into hydraulic presses, and they've basically just pulverized it with it. Even diamonds they put into hydraulic presses and managed to pulverize them. So it's pretty amazing. And some of them don't get pulverized, they just get sort of pushed completely into the metal of the press. So it's pretty cool to watch some of those. Even one I saw once, they were using a hydraulic press on a book, and they were basically returning the paper back to wood because they were compressing it so much that it just became a block afterwards. So you couldn't pull the papers apart anymore. They were completely fused together, and there was lots of water coming out of it when they were pushing it together. So usually you think that paper is very, very dry, but once you put it under enough pressure, you're going to push a lot of water out of it. So today we had these learning goals. We were to become familiar with different types of accumulators, which we did. We looked at the piston, the diaphragm, and the bladder kinds. And we even figured out how the piston accumulator works in specifics, and the same for the diaphragm and bladder accumulators. We also became familiar with pressure vessel safety requirements and these safety blocks that have to be placed if it's a group 2 pressure vessel, so more than 25 bars of pressure. And we've learned how a single acting cylinder works. So then we're going to continue next week with double acting cylinders. Yeah, that was all of my references for this one. So have a good weekend, everyone.